Section 6 involves solving rational expressions. Those are expressions in which the variable, the x, is in the denominator. So here we have our first example, 4 over x plus 1/3 equals 5/6. If we then multiply everybody by 6x, we get rid of all our fractions. And the result is 24 plus 2x equals 5x, which leads to 3x equals 24, or x equals 8. And of course, we can go back in and check. 4 over 8 is 1/2. 1/2 plus 1/3 is in fact 5/6. Second example, x subtract 5, subtract 36 over x equals 0. We're going to multiply everything by x to get rid of our one term that has a denominator. That gives us x squared, subtract 5x, subtract 36 equals 0. A quadratic that we can then factor to give us x subtract 9, x plus 4 equals 0. Putting each one to 0, solving, we end up with x is 9, x equals -4. Note how it's always the opposite. Here we had a -9 inside the parentheses. That became x equals 9. Here we had a plus 4 inside the parentheses. That became x equals -4. A ratio compares two values, such as 2/3, so it's a fraction. On the other hand, a proportion is a statement of equality between two ratios, such as 2/3 equals 6/9. If we have, in general, a situation where A over B equals C over D, then by cross-multiplying, we can get A times D equals B times C, and again, no fractions. And so, for example, here we have 3/4 equals x over 64. So we cross-multiply the 3 and the 64. They go on the left. The 4x, it goes on the right. And by solving, we end up with x is 48. So that is one part of section 6. Then we're going to have some example type problems. For instance, we're going to do what are called solving work rate problems. For example, working alone, Kim can paint a room in 4 hours. On the other hand, Greg can paint the same room in only 3 hours. So how long does it take the two of them to paint the room if they work together? So these we set up here as t over 3 plus t over 4. Note, the time is how long it takes to paint the room. The divisor part was how long it took each one of them. So Kim took 4, Greg took 3. And then the 1, it'll always be equals 1 in these kind of problems, is because we're talking about the time to paint one room. And so, if we multiply everything by the 12, we get rid of our fractions. Leaves us with 4t plus 3t equals 12. 7t is 12, or t is 12 over 7, which is about an hour and 43 minutes together. Another kind of problem for this section is when we need to square both sides when radicals are involved. For example, suppose we have 3x plus 4 equals 5. If we square both sides and then solve, so here we're squaring the square root part, and here we're squaring the 5. We end up with whatever was inside the square root, 3x plus 4, but no radical now, and on the other side is 25. And then we can go ahead and solve, and we have x equals 7. Squaring both sides can, however, lead to extra solutions that do not solve the original equation. Therefore, we have to check to verify that they actually are solutions or not. For example, suppose we had t plus 5 equals the square root of t plus 7. We're going to square both sides. So, on the one side, t plus 5 squared. On the other side, the square root of t plus 7 squared. Now, on the left, remember that any situation like that is actually calling to FOIL because we got t plus 5 times t plus 5. That's going to give us t squared plus 10t plus 25. On the right, we have just what was inside the square root. At this point, we're going to have to take all of this, move things around, so that now we have just the quadratic equals 0. In this case, we can factor t plus 3, t plus 6. Note, again, we had 9t in the middle, 3t, 6t, the inner and outer, give us the 9t. The 6 times 3 gives us the 18. The t times t gives us the t squared. So we factored that to get this, which gives us two answers, t equals negative 3 and t equals negative 6. Checking these solutions leads to, here, substituting in the minus 3 plus 5, minus 3 plus 7. Well, on the one side, we're going to end up, of course, with the 2. And on the other side, square root of 4, that's also 2. So check, that worked. Now, what about the negative 6? Well, here, negative 6 plus 5 is going to give us negative 1. Negative 6 plus the 7 gives us a positive 1. Square root of positive 1 is 1. And we end up with negative 1 equals positive 1, which is not true. Therefore, only the negative 3 was a solution. When squaring both sides, isolate the radical first. So, for instance, in this kind of situation where we have the square root plus the 3 equals the 7, we're first going to move that 3 to the other side before we square both sides. Otherwise, if we square both sides, we'll still have a radical after squaring. So here, again, that would have been similar to the situation up here, where we have the same thing twice, and we would have still had a middle term with the square root of 5x minus 3 in it. All right. So here's another example. We have square roots on both sides, but they're different. X plus 1 equals 1 minus the square root of 2x. We square both sides. See there, we still have a square root. But now what we're going to do is rearrange everything to get that square root all by itself on one side. And so 2x and the x, if we subtract 2x from both sides, it gives us the negative x. 1 and 1, subtracting the 1s, it gives those are gone. I'm left with negative x equals negative 2 times radical 2x. Squaring both sides, we get x squared equals 4. 2 squared is 4 times what was inside the radical 2x. And again, it gives us a quadratic we can solve. This gives us two choices, x and x minus 8, to solve for. And then finally, we sometimes have problems to solve in which the problem doesn't look like a quadratic, but it has the general form of a quadratic. In other words, it's got that squared term, and then it's got the term in the middle that just has an x, not an x squared, and then it's got a number all by itself. And we can do what's called a U substitution so that it now looks like a quadratic. It can be solved, and then it just takes a couple of extra steps. So for instance, let's suppose this is the problem we had. It doesn't exactly look like a quadratic because I got x plus 3, quantity squared, subtract 2x plus 3, subtract 8. However, this can be written as u squared minus 2u minus 8 if I let u equal the x plus 3. So again, if u is x plus 3, then that part becomes u squared. If that's x plus 3 is u, that becomes negative 2u, and then of course we still have the negative 8. Then I can go solve the problem that is u squared minus 2u minus 8. In some cases that will be factorable. Eventually this leads to answers u equals negative 2 and u equals 4. However, we did not want to know what u was. We wanted to know what x is. And so we will have to go ahead and solve x plus 3 is 4 and x plus 3 is negative 2, which gives us our final answers of x equals negative 1 and x equals negative 5. Now, we could have, of course, foiled this and distributed that and then combined all the like terms, but this is just an example to show you how a substitution can make a problem easier to solve. And here's our last example. Note, this has an x to the 4th and the middle term is an x squared. But in this case, if we go ahead and say u is x squared, we again end up with something that looks like a relatively simple quadratic. 4u squared minus 7u minus 2. Turns out this one is also factorable. u equals -2, u equals 1/4. So we come back, and well, u is x squared, so now x squared equals -2, and x squared equals 1/4, which our final answers when we square root both sides will be the plus or minus I, because it was a -2, square root of 2, and the other one will be plus or minus 1/2. And so that solves our various problems for section 6. Let us look at some more examples now. So what we're going to start off with is, again, a rational expression. It's got variables in the denominator. And honestly, these problems can take a little bit of room, so I'm going to go ahead and rewrite it up here. That'll make it easier to visualize what we're doing. So there we go. All right, now we want to get rid of our denominators, but we want to know what to multiply everything by. And so first, we're going to factor everything, or at least what we can factor. And so in the first one, x squared plus 4x minus 5 factors into x plus 5 and x subtract 1. Then here, it's already got its one factor, x minus 3. And then this last one, x minus 6, that will factor into x minus 3 and x minus 1. Now that I've factored, I can see that there are really three terms. We have x plus 5, x minus 1, and x minus 3. So now what we're going to do, again, to get rid of all of those fractions, is we're going to multiply everything times those three terms. Okay, so upon doing so, on this first one, the x plus 5s and the x minus 1 will cancel, leaving with just x plus 10 and the x minus 3. In other words, the only thing that's left, again, the 5s cancel, negative 1s cancel. In the next case, we're going to cancel out the x minus 3s, but that'll leave us with the x plus 5 and the x minus 1. And then in the last case, the negative 3, 1 will cancel, and the negative 1 will cancel, leaving us just with the x plus 5. Now, I still got work to do, but no denominators, no fractions at this point. So now we're going to FOIL everything. We're going to have x squared. The middle here will give me 10x. The outer will give me negative 3. 10 minus 3, that'll be 7x. And then subtract 30. Over here, we're going to have x squared again. And then we're going to have 5x subtract x. So that'll be a 4x. And then a negative 5. Now, I left off the sides because I wanted to emphasize that subtract means everybody has to end up as the opposite. So we're going to end up as a negative x squared, even though x times x was positive. The 5x minus the 1x gave me a positive 4x, but that's going to also be a negative. And then 5 times the negative 1 will give me a negative 5, but that has to become a positive 5. Over here, x squared, subtract 6 plus 5. This is subtract x, and then subtract 30. All right, now, anything that's the same on both sides is basically canceling. So I can take out 1x on both sides. I can take out that negative 30 on both sides. And let's see, what does that leave me with? That leaves me with a 7x subtract x squared, subtract 4x plus 5 equals negative x. So let's go ahead and move everything over. I'm just going to move it to the right side to make the x squared positive. 7 minus 4 is 3. So to the other side, that's going to be a negative 4x. The 5 will become a negative 5. Then I can factor. So I'm going to get an x subtract 5 and an x plus 1. Setting both of those equal to 0, I end up with x equals 5 and x equals negative 1. And so those become my two answers. Now, I do have to mention, you have to double check, because let's suppose that this had been a plus 1 instead of a minus 1. Well, going back up to the original factoring, that would have made this 0, because 1 minus 1, and then that doesn't work. You can't divide by 0. Likewise, if this one had been a negative 5 instead of a positive 5, that would have made this negative 5 plus 5, again a 0. Can't divide by 0. Now, it turned out in this particular case, it worked because we don't get those zeros, but it is something that you have to check. All right. Now, in the second case, I have 1 plus 2x minus 7 over x plus 3 equals 4x minus 1 over x plus 3. In this case, again, I'm going to go ahead and rewrite it. 1 plus 2x subtract 7 over x plus 3 equals 4x subtract 1 over x plus 3. I do not have multiple factors to worry about. I'm just going to go ahead and multiply everybody by the x plus 3. That gets rid of the fractions in both of those. So I'm going to end up with x plus 3. And then here, 2x subtract 7. And then there, 4x subtract 1. All right. So let's see. 2x and x, that's 3x. 3 minus 7, that's subtract 4. Here we have 4x subtract 1. If I move the 3x over, I'm going to have x subtract 1. Move the negative 1 over. I'm going to have negative 3 equals x. But here's the deal. Right there. If x is negative 3, negative 3 plus 3 will give me a 0 in the denominator. That's the only one I have, and it doesn't work. Therefore, this is a no solution. There is no x that will make the original problem true. And so there you have a couple of examples of rational problems. All right, now let's look at an example of a rate work problem. So, one pipe can drain in 10 minutes, with a smaller pipe takes 45 minutes to drain the tank. How long will it take to drain if both pipes are used at the same time? So, does it hurt to just kind of write things out? Rate of first pipe. Well, that's going to be T over 10. Rate of second pipe. Well, that's going to be T over 45. And if it's a little bit, it doesn't make sense entirely why we're doing this. This is the rate. So in other words, if one pipe can do it in 10 minutes, then if you're like, well, how many pipes at that rate, or how long would it take several pipes at that rate? That's why it's called a rate problem. In other words, the time is 10 minutes for each one pipe. In the second case, for the smaller pipes, it's 45 minutes for each smaller pipe. So if I had multiple smaller pipes or multiple bigger pipes, it would just be a multiple of that. Now, both pipes will be t over 10 plus t over 45, and then equals 1 because we're trying to drain one tank. Now, like always, we want to get rid of our fractions, so we're going to take our equation t over 10 plus t over 45 equals 1, and we're going to multiply everything by 450. And generally, I don't even worry about what's the lowest common multiple. I know both 10 and 45 go into 450, and so that's why I picked that. So this one is going to give us 45t. This one will give us 10t. And of course, this is the 450. So 55t equals 450, or t equals 450 over 55, which is about 8.18 minutes, which is also 8 and 2 over 11 minutes. And so there is a rate work problem. Now, a similar kind of problem. Here we have Kyung ran 7 miles this morning. After running the first 3 miles, she increased her speed by 2 miles per hour. If it took her an hour to finish her run, find the speed she was running the last 4 miles. So note, the first 3 miles she ran at some rate, and then the last 4, because she ran a total of 7, she increased her speed by 2 miles per hour. Now, time, we looked at this in an earlier section, is distance over the rate or the speed at which you're going. So, our, if you will, our T1, the first leg, well, they went 3 miles over some speed, some rate. The second half of the journey, a little bit more than half, but the second part, that was R plus 2. So the entire journey then would be 3 over R plus 4 over R plus 2 is going to equal 1. So in this case, again, similar to the other ones, we want to get rid of these fractions. So we're going to take everything and multiply it by both the R and the R plus 2. So with the 3, the R's will cancel and leave me with the 3R plus 2. With 4, the R plus 2s will cancel, and that'll leave me with the 4R. And then on the other side, we'll still have an R and an R plus 2, which, if you distribute, would give me R squared plus 2R. Okay, distribute here, and I have 3R plus 6 plus 4R equals R squared plus 2R. Move around everything, and I got 0 equals R squared minus 5R, subtract 6. This is factorable into R subtract 6 and R plus 1, which, again, you put each one of them. So in the one case, I'm going to end up with R equals 6. In the other case, I'm going to equal R equals negative 1, which really, when you get down to it, doesn't really make sense, because that would be like we're going in the opposite direction for our negative speed. So the question, however, is over the last 4 miles. So if she ran 6 miles per hour for the first part, then R plus 2 would give us 8 miles per hour for the last 4 miles. But very similar when you get right down to it to the great work problem. All right, let's look at a couple of them that have the square roots in them. So in this first one, we're going to square both sides. So on this side, 2 squared is 4, and then whatever's inside the square root, just write it out. I put the parentheses in because the 4 is outside of it. Now on this side, I'm going to square it, and that's like foiling, so that's going to give me, again, x times x gives me this. Inner 3 times x, outer x times 3, that gives me the 6x. The last 3 times 3 gives me the 9. Okay, go ahead and distribute. 16x plus 20 is x squared plus 6x plus 9. Go ahead and move things around. This one is factorable. Which will leave me with x is 11 and x is negative 1. And then we can check real quick. So 2 times 4 times 11 plus 5, does that equal 11 plus 3? Well, 4 times 11 is 44. 44 plus 5 is 49. So basically this side is going to have 2 times 7, whereas over here I have 14. So that does work. So go ahead and do the second one. We have 4 times negative 1 plus 5 equals negative 1 plus 3. So here 2 times negative 4 plus 5 is 1. The square root of 1 is 1. So we're going to have 2 times 1. Does that equal 2? Yes, it does. So both answers in that particular case work. All right, now in part B, I have 2 square roots. So let's go ahead and rewrite that one out. X plus 5 equals x minus 3 plus 2. Honestly, I recommend, and it's not a bad study technique, do all your work on scratch paper, and then when you like what you have, rewrite it again on the kind of paper that you would want to turn in. First of all, that makes it something that's legible for you and the teacher. But secondly, it makes it, you've gone over it one more time and it's nice and legible. All the steps are in order. You don't have things scratched out or anything like that. It makes it much easier to do. All right, so in this particular case, we're going to again square both sides. So on this side, all we're going to get is the x plus 5. But on this side, again, when we square it, we're going to get where we have to FOIL. So the first part, the square root of x minus 3 times the square root of x minus 3 will just give us x minus 3. The next part, well, I'm going to have 2 times this for the inner and 2 times that for the outer. So it's going to end up as 4 times x minus 3. This still has the square root. And then last, 2 times 2, that'll give me my 4. And again, if it helps, just go ahead and write it out that way. X minus 3 plus 2 times x minus 3 plus 2. Write that out. And so x minus 3, there's x minus 3. There's the outer, 2 times the square root of x minus 3. There's the inner, 2 times the square root of x minus 3. There's last, 2 times 2. All right, now we need to move a few things around. We do only have one x on each of these sides, so they're going to cancel out. Essentially, I'm going to have 4, subtract 3, so that's 1, and then subtract the 1 from both sides. I'm going to end up with 4 equals 4 times x minus 3, which I'm going to go ahead and divide both sides by 4. So now I have 1. The simpler I can make the problem, the better. Now I'm going to square both sides again. So 1 squared is just 1. Over here I now have x subtract 3. Move the 3 over, and I have x equals 4. So we can go back to the original problem and check. Now 4 plus 5 equals the square root of 4 subtract 3 plus 2. Well, 4 and 5 is 9. So I got square root of 9. 4 minus 3, it's 1. Square root of 1. Square root of 9 is 3. Square root of 1 is 1. So check, that did work. All right. So there is another example of squaring both sides to solve your problem. All right. So on problem 5, we're going to do, we're going to let u equal the square root of x, which means then that u squared equals x. So wherever we have an x, we're going to put in u squared, and wherever we have a square root of x, we're going to put in u. So our original problem then will become u squared plus u subtract 6 is 0. We go ahead and factor. This is going to be u plus 3, u minus 2, which will lead us to u equals negative 3 and u equals positive 2. But we don't want to know what u is. We want to know what x is. So that's going to give me the square root of x is negative 3 and the square root of x is 2. So squaring both sides here, x is 9 and x is 4. Now, again, since we squared both sides, we have to double check. And so in the first case, I would have basically 9 plus the square root of 9 subtract 6. Does that equal 0? Well, 9 plus 3, that's 12. 12 minus 6, nope, that's not going to work. Okay, again, 9 plus the square root of 9, well, that's 3, that's 12. 12 minus 6, that's 6. 6 is not 0. All right, what about in the second case? Well, here, we're going to have 2, no, excuse me, 4. The second one is 4. Square root of x was 2, but x is 4. Plus the square root of 4 minus 6. Does that equal 0? Well, 4, square root of 4 is 2. 4 and 2 is 6. 6 minus 6 is 0. That one did work. So the only one that is an answer will be the x equals 4. All right, in our next example, notice we've got x to the 4th and x squared. So in this case, we're going to let u equal x squared, which means then that u squared equals x to the 4th. So that'll give us u squared minus 14u plus 45 equals 0, which can be factored into u subtract 9 and u subtract 5. So u is 9 and u is 5, which means that x squared is 9 and x squared is 5. Square rooting both sides, this will give us x equals plus or minus 3. This one will give us x equals plus or minus the square root of 5. And so there are answers for that one. Now, one that's similar but looks weird because of what you see in the exponents, they're fractions, but we're going to do the same kind of thing. We're going to just say let u equal x to the 2/3. So notice how in each case, here the u equal the square root of x. Here the u equal the x squared. Here the u equals x to the 2/3. It's always whatever that middle term was. If this is going to work, that's the one you start with. So then u squared is going to be x to the 4/3 because it's just times 2 in the exponent. So that means now doing my substitution, x to the 4/3, well, that's u squared. X to the 2/3 is just u. This one ends up being u minus 5 and u minus 5 again. Or u equals 5, which then of course means that x to the 2/3 equals 5. Now the way you get rid of a exponent fraction is by doing the reciprocal. In this case, 2 times the 3 will give me 6, 3 times the 2 will give me 6, 6 over 6 is 1. So we don't usually write 1, so that's just going to be x there. On the other hand, we have 5 to the top part, you're cubing. The denominator part, you're square rooting. So square root of 125, which is also 5 root 5. And then one last example here. We're going to let u equal x minus 1. So then u squared equals x minus 1, like that. So then our problem becomes 1 plus 7 over u plus 6 over u squared equals 0. Then we take everybody and multiply by u squared to get rid of our denominators. And so I'll end up with u squared plus 7u plus 6 is 0. This one again factors into 1 and 6. So u is negative 1 and u is negative 6. Which means that in this case we'll have x minus 1 equals negative 1, and over here we'll have x minus 1 equals negative 6. And we know we're probably going to end up in trouble already because we've got square roots equaling negative numbers. But let's go ahead and go through the process. Here, x minus 1 square rooted squared gives us x minus 1. This one will give us 1. So move that. We have x equals 2. Here, we're going to get x minus 1 equals 36. So x equals 37. And if we plug them back in, we're going to find that, let's see, the top one, 1 plus 7 over 2 minus 1, square rooted, plus 6 over 2 minus 1, does that equal 0? Well, this is 1. This is basically 7 over 1. And this is 6 over 1. That's not going to equal 0. Because they're all positive. And in the other case, we're going to have 1 plus 7 over 37 minus 1 plus 6 over 37 minus 1. Does that equal 0? Well, this one, 37 minus 1 is 36. Square root of 36 is 6. So I'm going to have 1 plus 7 over 6. 37 minus 1 is 36. So that's going to give me 1 over 6. Again, everything is positive. So not going to work either. This one is a no solution. So took a while, but we finally got to our answer. And so that does it for section 6.